Let's take a look at an example of vertical circular motion involving a roller coaster loop. A 582 kilogram roller coaster car is traveling through a roller coaster loop. The car is moving with a constant speed of 16.9 meters per second at the top of the loop and 31.1 meters per second at the bottom of the loop. The radius of curvature at the bottom of the loop is 11.4 meters, and the radius of curvature at the top is 25.8 meters. In this problem, we'll calculate the centripetal acceleration of the car at the top of the loop, the net inward force, and the normal force at the top of the loop as well. To calculate the centripetal acceleration of the car at the top of the loop, I'll begin by writing my expression for the centripetal acceleration. In this problem, I was already given the tangential velocity or tangential speed of the roller coaster, and so there's no need to solve for it separately. Plugging in our values, we'll get an acceleration of 11.1 meters per second squared. To calculate the net inward force, all we need to do is multiply the centripetal acceleration, or the net inward acceleration, by the mass of the car. This gives a net inward force of 6,460 newtons. Now, to calculate the normal force at the top of the loop, we'll need to draw a force diagram on the roller coaster to analyze all of the forces pointing in the direction of the radius of the circle. At the top of the loop, I know that the gravitational force on the roller coaster car will be pointing straight down. I also know that the normal force provided by the track on the car will also be pointing downwards. That's because the normal force always acts perpendicular to the surface and acts against the object pushing against the surface, in this case, the car against the track. So in this situation, the net inward force pointing into the circle is actually going to be the sum of both the normal force and the gravitational force. So if I were to write this out, I would say that the net inward force is equal to that normal force plus the gravitational force. In this case, they're both positive because we define the direction into the center of the circle as positive always. And I calculated earlier that this sum has to be equal to 6,460 newtons. So if I were to subtract the gravitational force from both sides, right, I can solve for the normal force because I know that the gravitational force is just mg. And that'll be equal to 756 newtons. Now, I'd like to point out that the weight of the car this is substantially less than the weight of the car itself, right? The weight of the car is actually around 5,700 newtons. So the normal force in this case is significantly less than the weight of the car. This is the same phenomena that happens to the people inside of the car, right? The normal force exerted on the people by the car is going to be much, much less than the actual weight forces of the people themselves. And so this phenomena is what happens when you feel weightless at the top of a loop. The apparent weight, or your perceived weight, in other words, your normal force, is significantly less than your gravitational force at the top of the loop because of the centripetal motion. So because of this, you feel weightless, or that you have no weight. This is the same phenomena we saw in the elevator when the normal force was less than the weight force of the person in the elevator. Let's take a look at what happens at the bottom of the loop. All right, I'd like you to pause the video, take a moment, and see if you can solve for the centripetal acceleration, net inward force, and normal force for the roller coaster car at the bottom of the loop. Okay, now that you've had a chance to try it yourself, I'll begin by expressing the centripetal acceleration as I did before, giving me an acceleration of 84.8 meters per second squared. I can multiply this acceleration by the mass of the roller coaster car, just like I did before, to solve for the net inward force, or the centripetal force. And then to calculate the normal force in this scenario, I'll have to draw a force diagram as well for the cart at the bottom of the track. Now, at the bottom of the track, the force of gravity on the cart still points downwards, but assuming the track essentially comes to some sort of level or flat area, which it doesn't quite here in this photo, but assuming this is a more circular track, the normal force would point upwards into the center of the circle. And so in this case, the sum of forces in the direction of the radius of the circle would be the normal force pointing into the circle minus the gravitational force pointing out of the circle, right? So the positive Fn points into the circle, so it's positive, and FG points out of the circle, so it's negative. And we just said that this sum here has to be equal to this value we calculated previously. So that means the normal force here must be equal to this quantity plus the gravitational force plus mg, meaning the normal force here will be equal to 55,000 newtons approximately. All right, now as you can see, this is substantially greater than the normal force, or the weight of the car itself, right? The normal force here is substantially more than the gravitational force. And the reason is because the normal force has to overcome the force of gravity working against it now to provide enough centripetal force, or enough inward force, to keep this object moving in a circular path. And so this is the phenomena that results in a feeling of heaviness as you come out of the loop, right? If you've ever been on a roller coaster before, you feel heavier as you're coming out of the loop because the normal force on your car and on the body then of the person in the car is going to exceed your normal weight force. And so your perceived weight will be much greater than it actually is. This is the same phenomenon we saw in the elevator as well. When you were accelerating upwards, right, the person felt heavier than they did before. So hopefully this illustrates that when we have multiple forces pointing along the direction of the radius of the circle, we have to think of them just like we would normally. The sum of the forces, in this case making any force pointing into the circle positive and out of the circle negative. All right, this concludes our series of videos on circular motion and centripetal force. Please take a look at Canvas for practice problems to apply all of these skills and more.